Thank you, Mareike, for the introduction. First of all, I would like to thank the Hangai committee for awarding me with the Hangai Prize this year, and to say it's a very special honor to be talking in this plenary session with the whole audience. So I'm going to present the CAD-integrated parametric design cycle for structural membranes, which will include just an introduction of what I mean by the design cycle for structural membranes, which in short is just form finding, structural analysis, and cutting pattern generation. And then I would like to point out the advantages of the CAD integration with respect to a unified workflow, parametric design, and a few specific advantages in the methods. So the design cycle, like I said, consists of 3 disciplines. The first one is form finding. When we want to design structural membranes, we can't just draw a geometry and say this will work. We have to consider certain boundary conditions, so support conditions, topology, like where we will have a membrane, where we'll have an edge cable, and boundaries like that. And then we we have an idea of the pre-stress setting we would like to achieve, and can implement all that into a starting geometry, perform a form finding procedure, and then get an equilibrium shape that satisfies both pre-stress conditions that we set and the boundary conditions. Now, if we have an equilibrium surface with a given pre-stress, we need to perform structural analysis to make sure that certain safety requirements are met, and to make sure that also the serviceability is met, so that we don't have too large deflections and so on. And as you can see with the arrows indicated on the slide, there's of course an interaction between the form found shape and also the structural analysis, because what needs to be done if structural analysis shows that, let's say, the deformation is too big, then we need to go back and find a better shape. Then the third step would be cutting pattern generation. If we're happy with our shape that we found in the form finding procedure, and we know from structural analysis this will stand and this will withstand external loading, we need to make sure that we can actually manufacture the membrane structure. And in order to get a strength only through tensile forces, the membrane always needs to have a curvature, and mostly double curvature, which means that we can't just project the surface into the plane or develop it into the plane and then have our cutting pattern generation, but instead we need to perform an optimization, which again is a challenging task itself, to make sure that from flat stripes that meet manufacturing requirements, we can actually build up this 3D structure and also stay in the pre-stress settings that we wanted to have. Now, if we look at this design cycle workflow more in this workflow kind of way, we can see that the output from form finding will serve as an input for structural analysis and also for the cutting pattern analysis. So if I start thinking about the finite element approach and the modeling, it would be really nice to use it in this way, to use one model, have a form found one, and then sort of recycle it for structural analysis and cutting pattern analysis. And that's the idea of the CAD integrated workflow. And then, in addition to the 3 disciplines I've already presented, there's also mounting analysis. And by mounting analysis, I mean the real assembly of the stripes that I got from the cutting pattern generation, putting them together, putting them in my given boundaries, so the edge cables and the support points, and just checking how good was my cutting pattern. Do I still have a continuous surface, or do I have kinks somewhere? Do I need to deal with this for structural analysis as well? So, as you see indicated by the arrow again, this might be my new input for structural analysis, and so the cycle continues until I'm fully satisfied. Like I just said, the isogeometric approach is very beneficial if we look at this workflow, because we can work on one model, and I would just like to introduce what isogeometric approach means from a numerical point of view. So there's one main difference between a classical finite element model and an isogeometric one, and you see it on this slide, that we have a continuous curve, and if we apply the classical finite element approach, we have elements with linear edges, might be quadrilaterals, might be triangular elements, but they always just model our continuous surface in a facade type. So the information on the smooth curvature is lost, and we have some modeling error already. Now, if we use the isogeometric approach, we use a very smooth model that we get from computer-aided design and use that as an analysis model as well. So, as you see on the right side, the smooth geometry stays smooth, there's no facetting of the surface, and the description is just more accurate from a geometrical point of view. What this means for the finite elements is that the degrees of freedom in all directions don't really lie on the surface anymore like they do in the classical approach. You can see that on the left side for one element you have the degrees of freedom on the nodes, so on the surface. And for isogeometric elements, the degrees of freedom are on the control points. So I think many of you know this control point net that you get from the CAD program. And isogeometric analysis takes this control point net and uses that to define the elements and to put the degrees of freedom to then perform any analysis, really. This approach, so isogeometric B-rep analysis, has been implemented and applied to a tool called Kiwi 3D, which was developed at the Chair of Structure Analysis and the company Structure in Stuttgart, mainly by my colleague Anna Bauer and her colleagues then at Structure. And the idea of this unified workflow of having a CAD geometry, enhancing that with mechanical properties, also including the topology, and having all that on one CAD model was really realized in this Kiwi 3D tool. And I would like to show you in the following slides how the workflow really looks for membranes. So just to give you an overview, that's the basic idea you get. Many of you know Grasshopper, which is the foundation of the Kiwi 3D plugin. On the left side, the orange box shows you a geometry definition, very simple one. And then the blue boxes are the analysis boxes. So in this whole framework, we have the geometrical operations, which we can just use from CAD, and then the mechanical operations, which can just be applied from the classical finite element approach to the isogeometric one, because the mechanics don't really care where the degrees of freedom lie. The formulas will always just stay the same. So like I said, we start with the geometry, and the first step in our design cycle would then be to perform the form finding analysis. The mechanical background is the updated reference strategy, which was invented by Professor Bletzinger a while ago, and is a very established method. So this has been the basis of many structures we see, and is based on the force density method with an updating of the geometry, and then finds a form-found solution. So the structure I'm going to use to show you the application of the design cycle looks like this. It's in the beginning just the geometry. Think about the orange box again, just planes that are zigzagging around. So we have the boundaries, which are the support points, and then the areas in between, and of course edge cables to hold the membrane in place. This was modeled in a parametric way, so as you can see there are x, y, and z coordinates defining the surface, which can be changed in any position. And for the model, that just means it's very flexible. So if I changed, let's say, y1, I would just have a broader membrane in the end. And from a discretization point of view, again, this flexibility is possible because we use the isogeometric approach. So it doesn't matter how wide or how high I will make the structure, the discretization comes from the NURBS description, from the NURBS control point that and is therefore independent of the parameters I choose. So now here you already see the form-found structure. In the beginning, like I said, we just have the planes, then the updated reference strategy is performed, and we get an equilibrium shape for given pre-stress settings. And in addition to these geometrical parameters that I can choose, which are in this case the coordinates, I can also, with the isogeometric B-rep approach, use a parametric approach towards mechanical properties like the membrane pre-stress or the cable pre-stress. And that's something I then like to call parametric form finding, which is a very convenient way to test different parameter settings, like in this case the ratio of the pre-stress in the membrane to the pre-stress in the cables, which ranges from 1 to 5 to 1 to 10 and just changes the curvature of the edge cables. So by moving around in my workflow, I can just change these parameters, perform correct mechanical analysis, and look at the outcome, and therefore make a decision on what I want my structure to look like. The next step in our design cycle would then be the structural analysis. So now we say we are happy with the ratio of the pre-stress, we're happy with the curvature in the cables, and now we want to see if our structure can withstand external loading. And like I said, the unified workflow makes this very convenient. So we have the form finding results as a full CAD model and can use those results as an input for structure analysis. So in this Kiwi environment, I can just plug it into the next analysis. And as you can see, if we were to change something in the geometry on the very left side in the orange box, like make the whole thing a bit bigger or a bit smaller, I can forward these changes to the next analysis because they are all linked together. So looking at the mechanical side again, what I mean by structural analysis is geometrically nonlinear statical analysis. And here we just have a virtual work expression just to put you in the setting that we're working in. Now for this academic example, I just put a snow load of 0.5 kilonewton per square meter just to show the effect of the deflection. So on the top in light gray, you see the form-found membrane. Then a new uniform snow load was applied, and then of course the membrane deforms a bit, and we can in our Kiwi environment look at the displacements, look at the stresses, and identify problems if there are some. Go back to form finding, like I said, and like go another round in our design cycle. After structural analysis, just the cutting pattern generation needs to be performed as well. So again, we take the form finding results, which are fully available in the CAD environment, and use them as an input for the cutting pattern generation. In between, you see another orange box indicating there have to be geometrical operations done in between, Because of course, if I want to do a cutting pattern generation, I need to define the sort of stripes I want to build or the pattern that I'm trying to do. So I can take my form-found geometry, just apply trimming operations, finding geodesic lines and functionalities that any CAD program nowadays has, divide my surface into different parts, and then use those to calculate the cutting pattern. From a mechanical point of view, the variation of reference strategy is applied, and I would like to focus on this a bit because it shows how challenging just the correct mechanical formulation can be for these kinds of things. In this case, it's an inverse approach. So what I mean by that is we try to use something as a reference that we don't really know. We have the final 3D structure and want to know where did it come from. So in a first step, we would just do a simple projection to have some starting geometry, which is just a guess, and then use that really as a reference, like it would also be in the real building process. So we start from the plane and go up into the 3D shape. So the projected surface is then allowed to move, so all the nodes in the plane can move around, and an optimization process is run to find the best solution, which we can build up and find the right geometry and pre-stressed state. And the optimization takes into account the potential energy which arises from this erection process. So I have stresses because of the deformation, and I will have stresses in the final state from pre-stress. And the movement and the pre-stress state all add up to this potential energy, and if I manage to minimize this energy, I will have found the best solution for my cutting pattern. And doing this with the CAD integrated approach adds a few advantages. Like I said, I can just use standard CAD trimming operations, for example. And what we see here is the control point net that I was talking about, which has the degrees of freedom. And in the middle, you see one trimmed stripe. So this one was already separated from the other ones by just using cut operations. First of all, finding a geodesic line. And second of all, separating this by trimming from the rest of the structure. And with isogeometric B-rep analysis, I can now say the variation of reference strategy should just be applied to this one strip. Of course, I can also include the other ones, but just for you to get an idea. That still has the full CAD description as well. But through the trimming lines, I have identified my one stripe that I want to model now and that I want to investigate. And I could repeat this picture for the other stripes as well, obviously. So it doesn't matter which one we look at, they all follow the same routine. So for the example I was showing you, the cutting pattern would then look like this, just dividing it into these stripes with the standard cut operations, and then applying this optimization technique of variation of reference strategy would give me something like this. So I hope you can see this. The blue lines, the smaller areas, are just the simple projection that I was talking about. And then after the optimization has been performed, the shapes, of course, look a bit different. Now, in this case, I just want to point out that compensation hasn't been taken into account yet. That's why they look so big. But having in mind this workflow in the Kiwi 3D plugin, I can, of course, add to the steps that I'm performing. So I can also take that into account. Now, if we found the cutting pattern, we can perform mounting analysis. which is really just taking into consideration what we have. So we have a reference, we have a starting point, which are our cutting pattern stripes, and we want to build these up into the 3D shape and see what will come out of it. We have the support points and the cables as fixed boundaries, and in this case we see that the build-up structure looks quite good because I didn't have that much curvature in the structure itself, and like I said, there hasn't been compensation in this example, but I think you can get the idea. And thinking about the design cycle again, if we include this step now, it might be interesting to see what happens if I now do structural analysis on this mounted structure. So just go another step and add another box in my plugin. Next, I would like to focus a bit on the parametric design possibilities that we have. You see again the Kiwi 3D plugin. And isogeometric analysis and isogeometric design really makes it easier and more convenient to focus on this parametric design field. The first example is a membrane facade in Riyadh, which covers the National Library and consists of several membrane modules stacked on top of each other. And I used this as an example to show again the geometric parameters and also the mechanical parameters and how they have an influence, first of all, of course, on this small membrane module, but also how they change the large-scale appearance of the whole facade. So you see here the model in CAD with lengths A and B, and then the height of the module. It's supported on the very bottom and top point, and also on the sides. And like in the example before, the pre-stress in the edge cables and in the membrane can be varied because they're also modeled in a parametric way. And then investigating these different settings, like you can see now, just gives, of course, different modules, but also have a very big effect on the appearance on a large scale. The second structure that I would like to show in this parametric setting is the Sky Song structure in the USA, which is a very big one. And again, I just remodeled the structure with this parametric approach, gave the geometric entities different possibilities to play around with that. And of course, I still have the pre-stress in the membrane and also in the edge cables to also investigate how that might affect the overall structure. There's a little orange angle alpha on the bottom, which is the one that you will see in the next pictures. I changed that. So as you can imagine, if I copy this structure around a circle, this opening angle will, of course, have a big effect on the impact, because if I choose a large one, I have very large modules and don't get that many high points and low points. And if I make the angle smaller, I still have the same model, the same structure, don't have to apply new discretization or anything like that, because it's all coming from the NURBS description of my surfaces. And I can just investigate what happens if I have more towers and more low points. And this example is also included in the paper that I submitted for the Hangai Prize this year. Okay. So, finally, I would like to show a few examples that were produced in the membrane workshop last semester at TOM, which I'm holding together with Professor Schiemann in Munich. And this year, for the first time, we gave this Kiwi 3D plugins to the students and also let them play around with it just to see what the outcome might be. And their task was to design a membrane roof over the Kaltenberg Arena in Germany, which is an open-air arena for medieval night tournaments. And the outcome was really impressive. So the structures they found were really nice, and also in some cases they were able to go more into detail and to really investigate more different ideas than they used to in the past before they had this parametric tool. So I'm just going to show 3 of them. This is the first one, done by the students you see on the bottom. And you see this repetitive structure that they built. And they actually made the effort to also perform structural analysis and to do a cutting pattern generation, all in this one cut environment, and using the CAD integrated approach. Then the second one is quite different, as you can see. They first found these tree-like structures that they really wanted to have and called it the membrane leaves. So they had these very rigid and maybe a bit big beams supporting the membrane in between, and really tried to integrate this idea of using the parametric approach to have one module that you can then use to cover the whole arena. And this is a picture from the rendering they did, because that's also a point we have. If we have our structure from after form finding, after structure analysis as a full CAD model, of course, all operations like rendering or daylight analysis are also just available in the CAD software, and we can use them on our models directly. So the last one, again, you see certain modules that they designed and found a nice solution, I think, for the cover of this arena. Okay, so in conclusion, I showed you the advantages of the isogeometric BREP analysis for complex double curved surfaces, in this case membrane structures. We have a very high precision of geometry modeling in modern CAD software, and can use this through the isogeometric approach to have better mechanical models as well. I've showed you the unified workflow in the design cycle and pointed out the possibilities of parametric design, and I hope that you just got an idea of what I'm doing with this for structural membranes, and would like to thank you for your attention and the possibility to speak here.